morning, everyone. Thank you for joining us today. We live in a world that's constantly getting smaller, faster, and more powerful. We carry around these incredible devices in our pockets, but have you ever really stopped to think about how they're made? How we build circuits with parts that are thousands of times thinner than a single human hair? Well, that's the world of nanofabrication. It's a place of unbelievable precision and, frankly, genius. And to help us unpack this amazing topic, we have an expert guest with us. Welcome to the show.
Hello, everyone. Thank you for having me. It's a genuine pleasure to be here to discuss this important topic.
It's great to have you. So in our last get-together, we dove into the world of nanotechnology. That amazing science where materials at the atomic scale give us these brand new, incredible abilities. So as you can see here, the next logical and really the most crucial question is, how do we actually do it? How do we take all that incredible science and turn it into the technology we use every day? Let's start right there. What exactly is nanofabrication?
You got it. So think of nanofabrication as the master toolkit, right? It's the whole collection of processes and techniques we use to design and build structures, devices, and systems with features down at the nanometer scale. If nanoscience tells us what amazing things can happen at that scale, nanofabrication is all about how we actually make those things. It's the engine behind just about everything. Innovations in medicine, in energy, and of course, the entire multi-trillion-dollar semiconductor industry. But it's really more than just making things tiny. It's about controlling matter with such precision that you actually unlock brand new properties. A material that's an insulator on your desk might become a conductor at the nanoscale. And mastering that control, that's the real heart of nanofabrication. It's a fundamental shift in how we think about manufacturing.
That's a great way to think about it, not just size, but control. So when engineers are faced with this huge challenge, building at the nanoscale, I get the sense there isn't just one way to do it. The sources talk about two main philosophies that guide all this work. Could you break those down for us?
Yes, that's exactly right. Every single technique we use can pretty much be sorted into one of two big approaches, top-down and bottom-up. And this slide gives a perfect analogy to wrap your head around them. So on the left, you have top-down. This is the classic approach, the one that built the modern world. It grew out of microfabrication, and its real strength is its incredible ability to create these super regular, large-scale, perfect patterns. It's like being a sculptor. You start with a big, pure block of something, like a silicone wafer, and you just meticulously carve, etch, and remove material until you're left with your final, intricate design. We love it for its precision, which is exactly why it's still the absolute foundation of the semiconductor industry. But it can be pretty wasteful. Sometimes you're carving away 90% of a very expensive, highly refined material. And the tools, they are astronomically expensive. Now, on the other side, you've got bottom-up. This is a newer way of thinking, really inspired by that famous Richard Feynman talk. There's plenty of room at the bottom. This is the builder's approach. Instead of carving, you start with the basic building blocks, atoms and molecules, and you convince them to assemble themselves into the structure you want. The potential here is just immense. We're talking about building with atomic precision, almost no waste, and creating complex functional things that would be impossible to carve. The big challenge right now, though, is scale and control. Getting billions of molecules to all do the exact same thing perfectly is, well, it's a huge task. The future? It probably lies in combining the two, using top-down methods to build a framework, and then using bottom-up techniques to fill it in with all the cool functional parts.
Okay, that sculptor versus builder analogy really makes it click. So let's dig into that first one, the top-down sculpture. I see the main tool in that sculptor's toolkit is something called lithography. What is that exactly?
Lithography is, without a doubt, the heart and soul of top-down fabrication. Its whole purpose is to take a pattern you've already designed and transfer it onto a substrate, which is usually a silicon wafer. The best way to think about it is as a really, really advanced form of stenciling, but the stakes are unbelievably high. Every single transistor, every wire, every tiny component on a computer chip, and we're talking billions and billions of them, it owes its existence and its exact position to a pattern that was laid down by lithography. If that pattern is off by even a few nanometers, or if there's a single tiny defect, the whole circuit can just fail. It's the master blueprint. Every single step that comes after it, whether you're adding material or taking it away, depends completely on how perfectly that first stencil was made. The mind-boggling complexity of a modern CPU is, at its core, a victory of lithographic precision repeated hundreds and hundreds of times.
That makes total sense. So could you walk us through the most common type? I think it's called photolithography. How does that whole stenciling process actually work, step by step?
Absolutely. Photolithography is the undisputed workhorse of the entire semiconductor industry. It all starts with step 1. You take your perfectly clean silicon wafer and you coat it with a special polymer called a photorest. And that coating process is an art form in itself. You usually spin the wafer at thousands of RPMs to spread this liquid into a perfectly even layer, where the thickness is controlled right down to the nanometer. Next up, step 2 is the exposure. This involves a mask, and this isn't just any old template. It's a marvel of engineering, a piece of absolutely pure quartz with the circuit pattern etched onto it in chrome. A single mask can cost over $100,000. The wafer is then hit with a powerful blast of ultraviolet light from a massive laser delivered with incredible precision. That leads us to step 3, developing. A special chemical solution, the developer, is used to wash away only the parts of the resist that were exposed to the light. It's extremely selective, leaving the unexposed parts completely untouched. And what you're left with, which you see in step 4, is this tough little stencil of your circuit pattern. This stencil is strong enough to stand up to the really harsh chemicals, like acids or plasmas, that are used in the next big step, etching. And that's what carves away the silicon that wasn't protected, leaving your circuit features behind.
Wow, it really is an incredibly elegant process. Now, you mentioned it uses UV light. As we're constantly pushing to make everything smaller and smaller, transistors, components, does using light itself cause any fundamental problems? That is the critical question, and yes, it does. The biggest problem is a law of physics called the diffraction limit. Basically, light waves have a tendency to spread out when they pass through tiny openings, like the ones on a mask. This blurs the pattern. For decades, engineers found a really clever tricks to get around this, but eventually, they just hit a hard physical wall. The solution was this absolutely revolutionary technology called extreme ultraviolet, or EUV, lithography. This wasn't just a small step up, it was a multi-decade, multi-billion-dollar quest that a lot of people thought was impossible. EUV light at a wavelength of 13.5 nanometers is so energetic it gets absorbed by literally everything, even air and normal glass lenses. So the whole process has to happen inside a massive vacuum chamber. And instead of lenses, it uses this series of hyper-polished, multi-layered mirrors that are, no joke, the flattest surfaces ever made by humans. If you scaled one of these mirrors up to the size of Germany, the biggest bump on it would be less than a millimeter high. It is an almost unbelievable feat of engineering, and it is the only reason we have the 5 nanometer and 3 nanometer chips that power our most advanced devices today.
So EUV is the absolute cutting edge for making things in huge quantities. Is there anything even more precise out there? Maybe something that doesn't use light at all for more specialized work?
Yes, there is. For those times when you need the absolute highest resolution possible, we turn to something called electron-beam lithography. So instead of a flood of light and a physical mask, this technique uses a super focused beam of electrons to literally write a pattern directly onto the resist, kind of like an ultrafine pen. The advantages are huge. The resolution is incredible, even better than EUV, and it's maskless. That gives researchers amazing flexibility to test out new designs really quickly, but the drawbacks are also huge. It's a serial process. It draws the pattern one spot at a time, pixel by pixel. A single wafer that an EUV machine can process in about a minute could take a week or even longer with an E-beam. And to put that in perspective, a company like TSMC makes millions of wafers a month. You just can't build a global supply chain on a technology that's that slow. So its role is really critical, but it's a niche one. It's for researchers who are pushing the absolute limits of physics, for prototyping a single revolutionary new transistor design, and, this is key, for making the flawless, perfect masks that are then used in the EUV systems for mass production. So in a way, the slow, precise E-beam makes the fast, high-volume EUV possible.
That makes perfect sense. Okay, thank you for that amazing deep dive into the top-down world. Let's completely switch gears now and look at that other philosophy. It's time to talk about the builder's method. So now, instead of carving, we're building from the ground up. And I understand the inspiration for this comes less from engineering and more from nature itself. Can you explain that core idea behind the bottom-up technique called self-assembly? Self-assembly is just a profoundly powerful idea. The core concept is this.
You design molecules that will, if you put them in the right conditions, spontaneously organize themselves into the functional structures you want, all driven by their built-in properties. And as the slide says, we learned it all from biology. Think about it. A DNA double helix zips itself together, all on its own. A cell membrane, the very basis of all life, is just a bunch of lipid molecules that automatically arrange themselves into a perfect layer in water. Your entire body is built from trillions of cells that self-assemble into complex tissues. So in nanotechnology, we're trying to become architects of these tiny molecular forces. We basically design the blueprint into the molecules themselves. Then we just add a little bit of energy, maybe some heat, and we let physics and chemistry do all the construction work for us. It's an incredibly elegant and potentially a much more sustainable way to build things.
That connection to biology is just fascinating. So, can you give us a few concrete, practical examples of how scientists are actually using self-assembly right now?
Sure thing. First, we have something called block copolymers. These are basically long molecules made of different polymer chains that don't like to mix, like oil and water. When you put them down as a film, they separate themselves into these highly regular nanoscale patterns, like perfect little cylinders or layers. This can be used to create templates for new kinds of circuits, or for making ultra-dense patterns for the next generation of hard drives, which could potentially boost data storage by 10 times or more. A second, and truly mind-blowing technique, is DNA origami. This uses DNA's simple base pairing rules. A pairs with T, C with G. Scientists can design a long strand of DNA that, when you add shorter, staple strands, folds itself into almost any 2D or 3D shape you can imagine. These DNA structures can then act as programmable scaffolds. For instance, you could design a little DNA box that only opens when it detects a cancer cell, releasing a drug molecule it was holding inside. It's truly programmable matter. And finally, you have self-assembled monolayers, or SAMs. These are molecules designed with a head that loves to stick to a certain surface and a tail that stands straight up. They spontaneously arrange themselves into this perfectly ordered layer that is just one single molecule thick. This is a fantastic way to change the properties of a surface, maybe to make a medical implant more compatible with the body, or to create a sensor that will only bind to one specific virus.
It's incredible to think we can actually hijack the building blocks of life like that. Okay, so are there other major bottom-up techniques besides self-assembly? Let's start with this one called atomic layer deposition.
Yes, atomic layer deposition, or ALD, is another bottom-up technique that's all about perfection. It literally builds up films one single atomic layer at a time. It does this using a cycle of self-limiting chemical reactions, which gives it this incredible precision. This is absolutely essential for making the ultra-thin insulating layers in modern transistors. For example, if you want to make an aluminum oxide layer, you'd first pulse in a precursor gas, let's say TMA. It reacts with every single available spot on the surface, and then the reaction just stops. It's self-limiting. Then you purge all the extra TMA out. Next, you pulse in the second precursor, which is just water vapor. The water reacts with that first layer to form a perfect single layer of aluminum oxide. Then you purge the extra water, and you just repeat that cycle, TMA, purge, water purge, maybe 30 times, to build a flawless insulating film that's only a few nanometers thick. You just can't get that kind of perfect uniform coverage with any other method.
So ALD gives us perfect layers. What about the other precision method I'm seeing here, molecular beam epitaxy? How is that different?
Right, so molecular beam epitaxy, or MBE, is also a bottom-up technique, but it's a physical process, not a chemical one like ALD. You can think of it as atomic spray painting, but it's done in the cleanest environment you can possibly imagine. A vacuum so pure it has fewer stray molecules than deep space. Inside this chamber, you have sources of elements, like gallium and arsenic, and you heat them up until they evaporate, atom by atom. These atoms form molecular beams that travel to a substrate. The key word here is epitaxy. It means the film grows in perfect crystalline alignment with the substrate it's landing on. This lets you create what are called heterostructures, where you can layer different types of crystals on top of each other, one atomic layer at a time. This layering creates unique quantum effects, which is exactly what makes things like high-frequency transistors for 5G communication possible, not to mention the semiconductor lasers in every Blu-ray player and fiber optic cable.
The level of precision in these techniques is it's mind-boggling. Now, you've mentioned the environment where all this work happens a couple of times. It really sounds like all of this incredibly delicate work, both top-down and bottom-up, needs a very, very special place to happen. Why is that specialized environment, the clean room, so absolutely critical? The clean room is completely non-negotiable, and the reason is all about scale. For you and me, a speck of dust is invisible, right? We don't even notice it. But at the nanoscale, that exact same speck of dust is a catastrophic device-killing boulder. Let me put this in perspective for you. This first slide shows the particle count in a normal office. In a single cubic meter of air, that's about the space under your desk, there are well over 1 million particles larger than half a micron. We're talking dust, skin cells, fibers from your clothes, you name it. Now, a key part of a modern transistor is about 5 nanometers wide. That means a single speck of dust is 100 times bigger. If one of those landed on a wafer during fabrication, it's like dropping a house on a city block you were trying to build. It could block the light during lithography, it could stop a chemical from etching properly, or it could short-circuit 2 wires. The entire chip, worth thousands of dollars and days of work, would be completely ruined. It is a zero-tolerance game. Okay, now look at this next number. This is the particle count in a state-of-the-art nanofabrication cleanroom, what we call a Class 1 cleanroom. In that very same cubic meter of air, there are fewer than 10 particles of that size. It is one of the absolute cleanest environments ever created by humanity, literally hundreds of thousands of times cleaner than a hospital operating room. This extreme, almost unimaginable level of cleanliness is the only way to get a decent yield, meaning to produce chips that actually work. And that's exactly why building and maintaining these facilities costs billions and billions of dollars.
And maintaining that level of clean takes some pretty amazing engineering. First, the air itself isn't just filtered once. The entire ceiling of the main production area is often one giant bank of these HEPA or ULPA filters. Clean air constantly flows straight down in what's called a laminar flow, pushing any potential particles down into vents in the floor. Second, there's positive pressure. This is a simple but brilliant idea. It means the pressure inside the cleanroom is slightly higher than outside. So if there's ever a leak or you open a door, clean air always pushes out, preventing dirty air from getting in. And finally, you have the really strict protocols, because the dirtiest thing to ever enter a cleanroom is a person. You have to wear those iconic bunny suits made from special non-shedding material. You go through multiple gowning rooms, and right before you enter the main area, you stand in an air shower, a little chamber with air jets that blast you from every direction to knock off any last tiny particles. It's an incredibly disciplined environment, and it's all just to protect those tiny, tiny structures.
It's like a whole other world. Okay, so let's tie all of this together now. From the sculptor's top-down methods and the builder's bottom-up approach, all the way to the pristine clean rooms where it has to happen. What is the big picture here? Why is mastering all these nanofabrication techniques so important?
When you zoom out, nanofabrication is what gives us the tools to turn the promise of nanotechnology into our reality. These two different philosophies, the subtractive, ultra-precise top-down approach and the constructive, nature-inspired bottom-up approach, are the engines that power our entire technological infrastructure. Every advanced computer, every smartphone, every life-saving medical device relies on our ability to build things at this scale. And because of that, mastering these techniques has become a matter of immense strategic importance. This isn't just about being economically competitive anymore. It's about national security, scientific leadership, and our ability to solve the huge challenges of the future. Access to advanced fabrication facilities, or fabs, is now seen as critical national infrastructure, right up there with power grids. And that's why you see nations all over the world making it a major geopolitical priority to build up their own domestic capabilities in this area.
That really puts this whole field into a global context. Thank you so much for that incredibly clear and comprehensive overview. You've given us a fantastic look at the immense skill, precision, and strategy that's required here. Before we wrap things up, let's just do a quick recap of the key takeaways from our conversation.
So, to quickly summarize, we've learned that nanofabrication is really the essential how-to of nanotechnology. It's the engineering that brings the science to life. It's done mainly through two opposing but totally complementary philosophies. You have the top-down approach, which is like a sculptor carving features out of a block of material, with lithography being its star player. And then you have the bottom-up approach, which is more like a builder, using things like self-assembly to build structures from the atom up. Both of these are absolutely essential, and all of this incredibly sensitive work has to happen inside the pristine, particle-free environment of a clean room.
So we now understand the philosophies of the sculptor and the builder. But once these incredible structures are built, how do we even know they're really there? How do we see them? Well, that is the perfect setup for our next session, where we will explore the world of characterization techniques, the incredibly powerful microscopes and tools that let us see, measure, and analyze the nanoworld. Thank you again for joining us today. To continue exploring these topics, make sure you subscribe to our channel, Tech AI and Beyond, where you'll find every one of our sessions. And we'll leave you with this final thought to chew on. As we continue to design the very fabric of our future, atom by atom, will it be the meticulous sculptor, the intelligent builder, or some new hybrid of both that truly defines the next generation of technology? Thanks for listening.